So the right-hand motor rule, by the way, those of you who are watching this online, I have to be standing up and moving around the class. You're going to hear my voice fade in and fade out. Sorry, this is just a lesson where I have to stand up quite a bit, and I'm not going to pause the video every time that I do. So here's the question. Suppose I have a wire carrying current through a magnetic field. I'm going to pause the video right now to show you guys a video in class. So Faraday found that a wire that carries a current through a magnetic field undergoes a force. What direction? Here is how you figure it out. This is the right-hand motor rule. First of all, look at my diagram. What do those dots mean? Which direction is that magnetic field? What did we say? Okay, magnetic field's coming out of the page towards us. And what direction is the current? See the battery on the left-hand side? What direction is the current flowing? So let's draw in little arrows here. First of all, let's bring this back, Mr. Dueck. Draw a little arrow pointing to the right. And because I'm going to be doing this on my screen behind me, all of you right now lift your papers or your binders up so they're vertical, so they're all in the same orientation. Hold your paper up vertically. Seriously. Okay? Here's the rule. You point your right thumb in the direction of the current. All of you right now point your right thumbs in the direction of the current. You're going to have to get a bit flexible here. Extend your hand like you're going to give a high five. Point your fingers in the direction of the magnetic field, which means if my thumb is still pointing right, I have to bend my hand like this. Your palm points in the direction of the force. Now, by the way, Joe, don't bend like this. That's why, like you're giving a high five. Your hand is straight. You got to bend like this. Which way is my palm pointing right now? Down the page. This wire will experience a force down the page. This is the right-hand motor rule. Actually, John, look, what we're really doing is we just multiplied vectors together, but I'm not teaching it to you that way. But for what it's worth, we know how do you add two vectors? Draw them. How do you subtract two vectors? We don't. We add the opposite. How do you multiply vectors? There's two ways, depending on whether you want a vector answer or a scalar answer. If you're multiplying vectors and you want a vector answer, it turns out that direction times that direction is that direction. That direction times that direction is that direction. Sorry, people at home can't see what I'm doing with my hand, but that's fine. We're doing what's called a cross product. We need to practice this. Example 7. What direction? We have a current. We have a magnetic field. What direction is the current into the page? What direction is the magnetic field? So all of you, hold your papers vertically like me. Point your thumbs into the page. Extend your fingers like you're going to give a high five. And point your fingers in the direction of the magnetic field. I need to rotate around for me because I can. Yes? Which way is the net force? Which way is your palm pointing? Up the page. Can you get out the right-hand rules questions handout? If you don't have it, if you can't find it, it's very important that you tell me because this is how I'm going to be explaining it and you need a bunch of examples. So the second handout that I gave you on the same day. Okay, number 1. Oh, by the way, not only does this work with a wire carrying current, this works if you just have a moving charge in a straight line, because all a wire is a bunch of charges moving in the same direction. So let's isolate a charge, like in number 1. We'll start to look at how a particle accelerator works. Yeah, that's the right handout. It says 2 particles, x and y, of equal mass but different charge, enter a uniform magnetic field with the same velocity. Actually, you know what? Go back to lesson number 1. I think I wanted to do the question on the next page still. Double check. Yeah, I did. One more page here. Example 8. Sorry. Then we'll go into the big handout. Example 8. This is where I was going to say, turns out you can also use this same rule if you're firing individual charges, particles, charged particles, instead of wires. they'll also undergo a force and be deflected. So an electron, wait a minute, I've got a problem. Our rule works for current, and current is which way positives would flow. Okay, Braden, you with me? Back on example 8? Okay. Which way is this electron traveling? Mathematically, which way is that the same as a proton traveling? Let's all of us right now, above the word an electron, let's write proton traveling left. So this electron is being fired from an electron gun. We learned about electron guns a couple of units ago. And suddenly it hits a magnetic field. Which direction is this magnetic field? What do those X's mean? Into the page. So all of you point your right thumbs, to the left. Extend your fingers like you're giving a high five into the page. Into the page. Now, not like this. High five, yes, you got to move your elbow. This is why you weren't here. This is why I told you guys, those people that do it like this, all tucked in, get it wrong. Get your arms out. Hey, which way are your palms pointing? Which way is the net force? Which way will this electron be forced? Down the page. Let's go back to now the right-hand rule questions. Number 1. It says 2 particles of equal mass but different charge enter a uniform magnetic field with the same velocity. What best compares? Now, I haven't yet told you how the size of the charge determines how much it gets deflected, but we can certainly figure out which way is positive, which one's positive, which one's negative. Let's assume they're positive. What direction are they traveling? Point your thumbs to the right. Which way is that magnetic field? Into the page. If it's positive, which way will it get deflected? Up. So which one is positive, X or Y? X. So I'm going to go like this. X is positive, no, no. It's either A or B. I haven't taught you this part, but for what it's worth, what do you think would get deflected more, a bigger charge or a smaller charge? What would make sense? What do you think would feel a bigger force, a bigger charge or a smaller charge? That's a bigger charge. Okay, bigger charge. I haven't told you that. Some of you were guessing small. Bigger charge undergoes a bigger force. You know what? Which one's getting deflected more, X or Y? Which one's getting deflected at a sharper angle? Which one's getting deflected more? X. X has a bigger charge. X has a bigger charge. You know what? The correct answer is A. We'll get more into that part of things in a few minutes.
So what are the X's and dots? Like X's into the page?
Yeah, you were away,
Yeah.
and you clearly didn't watch the video lesson. That's on you. X is the tail feathers of an arrow going away from us into the page. Dots is the tip of an arrow pointing towards us out of the page. Number 2, which is actually on the next page because it got cut out. Anyways, number 2. Okay? Which way is the current? Which way is the magnetic field? Answer number 2 on your circle what you think is the correct answer. Don't blur out an answer. See if you can figure this out. Ready, Akemi? Ready, Akemi? Point your thumb up. Which way is the magnetic field? Point your fingers that way. Which way is my hand pointing? Into the page. C. Number 3. Okay, here's a 3-dimensional diagram. We're going to have to use our imagination just a little bit, but that's okay. Proton, hey, that's a positive. I'm good with that. Proton is traveling kind of up and to the right into the page away from me. I'll imagine that. Ooh, which way is the magnetic field? Which way do magnetic field lines always point? From what to what? You know what? Let's draw a couple of magnetic field lines in from north to south, and let's even put a capital letter B underneath here. That's our magnetic field. Okay, try number 3. A, B, C, or D. Don't blurt out an answer. See if you can get this. Ready, Vlad?
Nope.
Yeah, I know. Ready? Hold your paper up vertically to match mine. Right thumb, you know what? This proton is traveling kind of that way. Yes? Into the page? Yes? Yes? Which way is the magnetic field?
Right.
Extend your fingers, extend your right fingers that way. Okay? Not like this. The proton's going this way, into the page, right? Which way is your palm pointing?
Down.
What's the correct answer? B. Number 5. Number 5. All of us right now underline the word electron. That's hugely, all of us right now underline the word electron. All of us right now, every single one of us right now on number 5, underline the word electron. Okay? Which way is the electron traveling? We don't deal with electrons. What's that the same as? A proton traveling which way? So point your thumbs to the left. Which way is the magnetic field? Down the page. Okay? Thumbs left. Magnetic field down the page like that. I got to bend a bit. What's the correct answer? Out of the paper. Yeah. Thank you, Kevin. Help him out. Number 7. Number 7. Okay. First of all, Sebastian, Marshall, what direction are the X's, the magnetic field in number 7? I can't hear you, sorry? Into the page. Okay, and yeah, I guess I have to use your imagination. What we have here is positives going this way, and then this is a conducting liquid, so the positives are just traveling through the water or whatever this is. The current right here, the positives are traveling which way? The arrow helps you out. So which way will they get deflected? Point your thumbs to the right. Which way did you say the magnetic field was? Into the page. Which way will pause? Into the page. Yeah, you got to align it with your paper, Vlad. You can't be doing it like this in your head. Which way is your palm pointing, Vlad, my friend? Positives will get deflected up. Which way would negatives get deflected? Let's see. Let's see. Negatives traveling to the left. That's the same as positive traveling which way? To the right. Point your thumbs to the right. Which way is which way will the negatives get deflected as it turns out? Also towards the surface. But the reason is because they're traveling in the opposite direction of the positives. If they were traveling in the same direction as the positives, they would get deflected down. But they're not. What this would do, right? So if the negatives were traveling that way, if positives get pushed up, negatives would get pushed down. But because they're traveling to the left, they actually also feel a force up because electrons traveling to the left is the same as protons traveling which way? To the right. So if you go like that, here's what would happen. You'd get a convection current like this. This is an electric stir. This would mix this up electrically with no moving parts. Number 11, which is actually on the next page. Which way? Try answering this on your own. Without blurting out an answer. Graydon, which way?
Is it C?
Is it C, Graydon says. Is he correct? He is. Okay. You got to start, Vlad. It's about time you figure it out. Hold your paper facing you because you can't.
I did that. I
Okay.
got up. I was trying to determine
So, you ready?
Knees means up.
No problem. Ready? Right thumb. Right? Magnetic field. Bend with me, bend with me, bend with me. Into the page. Toward the top of the page. Right? Don't feel bad.
I don't.
You're not the only one here. Hey, number 12. Ooh, now they gave me a full circuit. Wait a minute. In that bottom wire, which is the one that's inside the magnetic field, which way is the current traveling? Up to the right, away from us, or down to the left, towards us? Well, let's follow the current. Here's the current. Here's the current. You know what? I think the current is up to the right, away from us. Yes? What direction is the magnetic field? Magnetic field lines always point from what to what? So which way will this wire be deflected? Up, down, left, or right? Try and figure it out on your own. Right thumb, magnetic field, B, down.
Who has issues now, Kevin? I don't know. Explain what you think. But always going that way.
Absolutely, Vlad. You are correct, sir.
Buddy, you're missing out on life.
Number 13. This one's very cool. Number 13 says this. 13 is also actually on the next page. Sorry, it's just the way this thing printed. The diagram shows a current flowing in a circular coil located in a magnetic field. The magnetic force acting on the coil will tend to cause it to A, expand, B, contract, C, move up the page, D, move down the page. You know what? This is a tricky one. Let's look at the top of the circle first of all. Which way is the current flowing at the top of the circle? To the left? Point your thumbs to the left. Which way is the magnetic field? So which way will the top get exerted, a force exerted on it? So the top's going to get pushed down. So right now I'm thinking B or D. Now Cole just made a good jump. Cole, look at the bottom. Which way is the current moving on the bottom? Point your thumb to the right. Which way is the magnetic field? Oh, which way will the bottom get forced? And in fact, what you've just done is you've developed a compression shrinking magnetic ray thing. I don't know. What do those X's mean? Tail feathers of an arrow going away from you into the page. Right? Number 15, also on the next page. Okay. Ready? We can't do all of this yet, but we can do part of this. Number 15 says an electron traveling at high speed enters the magnetic field as shown. That's the first picture. A proton traveling at the same speed then enters the magnetic field. Which of the 6 choices best illustrates the path the proton will follow? We can't quite answer that, but I can narrow it down to 3. Which 3 letters could only be a proton if the electron got deflected in that path? R, S, or T. Because if an electron gets deflected down, a proton has to get deflected up. Okay. By the way, T, but you don't know that. Because a proton has so much more mass, it doesn't get deflected as fast by the same force. Electrons are easier to deflect. They're lighter. Number 20, which is also on the next page. Try number 20. Try number 20. So here's a beam of charged particles. By the way, this is how you can split up a beam into positive and negative particles. Very easy to do. Particles, yeah, there you go. It's very easy to do. Let's assume they're positive to the right. Great, and which way does X's mean for a magnetic field? Into the page. Which way will the positives get deflected? Which way will the negatives get deflected? Yes, yes, no, no, yes, no, sorry. No, yes, no, yes. Correct answer, B. Now, there's one thing I haven't told you yet. And this leads us to number 21. It turns out it's not enough to simply have a current, or moving charges, and a magnetic field. It turns out the only way the wire or the moving charges feel a force is when they cut across magnetic field lines. If they travel parallel to magnetic field lines, like in number 21, there is no force. This thing is going to keep going in a straight line. What Faraday and other scientists found was actually when they're perpendicular to each other, which is why we're having to do this right-hand rule thing. I don't know if you've noticed, it's actually the only way that we can go 90 degrees, and get a 90-degree answer. That's why we're using our right-hand rule. It turns out it's when all are perpendicular to each other, that's when you experience a force, which leads us back to our lesson. Back to here. So hopefully you've got the hang of figuring out the direction. And hopefully you agree with me from the video that I showed you, hey, there is a force. Question is, how big? How big? Here is your first equation for this unit. Turns out the magnetic force on a moving charge, I'll call it FB for B magnetic field, is equal to how big the charge is, how fast it's moving, and how big the magnetic field is, where how fast it's moving and magnetic fields are both vectors, velocity and magnetic field. Except we need to add one more thing. These need to be at right angles to each other. If that charge isn't crossing magnetic field lines, if it's traveling parallel to magnetic field lines, it will not undergo a force. It will only undergo a force as it crosses magnetic field lines. Great question. Sometimes, I wrote, the charges don't move perpendicular to the magnetic field. If that's the case, then you have to use components, which we did for forces, which we did for projectiles. We won't actually do that in Physics 12. I won't test you on that. I'm showing it to you. But in actuality, the correct equation is really this, Brett. It's Q, V, B, sine theta. But if theta is 90 degrees, the sine of theta is 1. And so you have QVB times 1, or just plain old QVB. Oh, and if theta is 0 degrees, because they're parallel, sine of 0 is 0, you have QVB times 0. Oh, no force. Okay. So, for what it's worth then, Brett, we're going to look at the situation where there's a maximum force, and it's experienced when the charges are moving perpendicular to the magnetic field, and that's why we need to bring out this right-hand rule, because we're having to do math. This is the first time that we've done vector math with stuff that is not in the same direction. You may recall me ranting during the projectiles and forces unit, direction, direction, direction. How can you put a vertical with a horizontal? Well, here, using a cross product, multiplying vectors using a right-hand rule. So let's apply this just a little bit. A proton moving that fast enters a 0.15 Tesla magnetic field at, oh, here's the key thing, right angles. So this is perpendicular, so this is going to undergo a force. What's the net force? Let's call that part A, and then part B says what's the acceleration? A. F equals Q V B. This is the force on an individual charge. And once we've established this, we can extrapolate this to a force on a wire pretty easily. Next class. Q. This may sound familiar. It's a proton. Yes, it's on your sheet, although you may still have this memorized. 1.6 times 10 to the negative 19. Oh, and if it's an electron, don't include the negative. You've already done the direction with your right-hand rule, so you don't need to put a negative in. V, speed, 1.7 times 10 to the 6th. No, if I ask you for, you use the right-hand rule if it's direct. If I ever ask direction. Here, I didn't ask you for the direction. That's one of the net force magnitude. B, 0.15, pretty strong. What's the net force on this proton? Now, it may not seem big, but remember, a proton has such a little mass. This is a huge force, because when we calculate the acceleration in just a second, it's going to be big. What'd you get? 4.08 times 10 to the negative 14 units. Force. Newtons. As soon as it hits that magnetic field, it's going to feel that big a force. Rob, what does B want us to find? Hey, if I know the force, how can I figure out the acceleration? Oh, A equals F over M. The F is 4.08 times 10 to the negative 14. Mass. It's a proton. 1.67 times 10 to the negative 27. Try crunch it out. You get a huge acceleration. Do you get 2.4431 times 10 to the 13th? Yep. 2.44. Wait a minute, Mr. Dueck. Isn't that faster than light? And I thought nothing can go faster than light. Okay, first of all, that's not a speed, it's an acceleration. Yes, if that occurred for 1 whole second from rest, it would be traveling at 2.4 times 10 to the 13th meters per second squared. It's not occurring for 1 whole second. In fact, it's occurring for a split second. But it's a big acceleration. It's a huge force. Big deal. Some neat applications. Next handouts. Lesson 2. Quiet, please. So recall, we just finished saying the magnetic force on a particle moving perpendicularly to a magnetic field is calculated by, we said the force is Q V B, as long as they're at 90 degrees to each other. So, example 1, consider this electron. Put your pencils down once you've written that force equation down and look up. Chase, which way is this electron traveling? We don't deal with electrons. Which way is a proton mathematically traveling the same way? Yeah. So which way is a proton traveling, Chase, mathematically? To the? So all of you, point your thumbs to the left. When this electron hits the magnetic field, which way will it be deflected? Down. Don't write this down just yet. Just watch. Don't write this down. Just watch. Look up. So when it gets here, it's going to get deflected down, which means a few minutes later it's going to be traveling that way, which is the same as a proton traveling up and left. Point your thumbs up and left. Which way will this electron be deflected now? Down and left? Yes, kind of. In fact, it's going to get deflected this way, yes? And for a split second, it's traveling in that direction. That's the same as a proton traveling straight up. Point your thumbs straight up. Magnetic field into the page. Which way will it be deflected now? To the? To the left, which means it's going to get bent kind of that. Ooh. Did anybody see it? What shape is it going to trace out? Write that down. It turns out that particles, if they enter a magnetic field, because as soon as they're not locked inside a wire like current, they're free to be deflected. As soon as they start to deflect, now their velocity has changed, their deflection angle is going to change, they're going to get forced into a circle. A half circle, but we'll call it a circle. Why is that so important? What shape is that path tracing out? You just answered it. No. Try this again. You just wrote it down. What shape is that electron tracing out?
Circle.
Which direction is my net force? Toward the?
Middle.
Ah, some good review. It means that I can say this. Magnetic force, this is important, equals circular. Guys, with me? Circular force. Remember, for orbits, we right away said that gravity equaled circular. For particle deflection, we can say magnetic equals circular. Where magnetic force is QVB not a very good perpendicular, equals mass, you know what? We're going to use the V squared over R, not the 4 pi squared R over T squared. We can push charges into a circle. Oh, by the way, hey, Mr. Dueck, what happens? Turns out one of the V's cancels. And you get QB equals MV over R. I don't memorize this. What I memorize is if I'm moving in a circle, I know magnetic force pushed me in a circle. But how many different variables are there in my final little equation there? 5. If I give you any 4, you can find the 5th one, and that's going to be fair game on a test. But what we've actually done is we have designed a particle accelerator. There's a reason why the Large Hadron Collider is built in a circle. Because of this. Watch.